Hi, welcome to this video. I'm going to review another article of this special publication of economic geology. This is chapter 10. The title is Complex Petrogenesis of Porphyry-Related Magmas in the Cowal district, Australia. Insights from laser ablation Zircon imaging. Unlike other belts, Cowal formed in an intraoceanic arc that evolved over time, picking up crustal signatures as it matured. So the result was the magmas that were recharged, contaminated, and chemically steered and produced something totally unique here. These researchers used zircon and amphibole chemistry to extract temperature, pressure, and redox conditions of those magmas. So what's new about this study is that it shows that hybrid crustal or crust contaminated magmas, not just mantle melts, can be incredibly fertile, and it links their evolution directly to fault zones and mineralization pulses. This study challenges the assumption that only typical adacitic or mantle-derived magmas are fertile, and emphasizes on the importance of long-lived hybrid systems in crustally influenced arcs, which could be applicable to other transitional arc settings worldwide. As we dive into the analytical framework of this study, let's first explore the methodology. The researchers began with carefully selected field samples, and they processed the samples by separating zircon crystals. They've used CL imaging, light microscopy, to reveal internal growth zones and zircon cores. Then they applied two high precision techniques: laser ICP-MS spot analysis to get point by point trace element data, and raster imaging to map element distributions across entire zircon grains. For this analysis, they calculated trace element ratios like europium and cerium, and also gadolinium, ytterbium to infer redox, hydration, and fractionation states. Titanium in zircon thermometry also have been used to provide crystallization temperatures, while zircon oxybarometry revealed oxidation conditions of the original magmas. And finally, they filtered and visualized all this data using IOGAS and ArcMap to position chemical zoning with magma evolution and align those two with each other. So what made this study truly innovative? First, their use of zircon raster imaging allowed them to detect subtle geochemical shifts across crystal zones. By interpreting growth zone specific signals, they reconstructed multiple magma recharge events. They also identified fertility enhancing signatures like high cerium and europium concentrations, which concentrated at zircon rims and linked them to late stage fertile magma pulses. And perhaps most significantly, they developed a powerful Zircon-only workflow to evaluate porphyry fertility, the one that's especially valuable when traditional whole rock geochemistry is compromised by alteration. So altogether, this study not only refined how we understand porphyry systems, it refined how we read zircons too. When people think of porphyry, copper, and gold, they think of Andes or maybe British Columbia or Mongolia, magmatic arcs in those parts of the world, but one of the most geologically interesting porphyry belts are here in southern Australia. This is a regional map showing the Macquarie Arc, which is hosted within the Lachlan origin, part of the broader Tasmanian East system that stretches across eastern Australia. It's formed in the Ordovician during subduction along the Gondwanan margin, and as you can see on the plate A of this image, it's now split into three major belts: Johnny Narromine, Melong, and Rockley Galgong. These belts preserve volcanic and intrusive rocks from an ancient island arc system that has since been dismembered. Now, let's zoom in to see where the mineral action happens in panel B. Here we have North Sparks region, which is home to Australia's only black cave mine for copper gold, and it's a classic alkalic porphyry system. Then we have Cowal igneous complex. Here we can find Endeavour 42 and Marsden, which are epithermal and porphyry systems with textbook magmatic hydrothermal features. And finally, we have Cadia district, which is one of the world's largest gold producers. Cadia is a global model for porphyry exploration in convergent arc settings. And these mineral systems are not random. They align with discrete igneous complexes, which are quite often granodiorite or monzonite in composition, and each reflects different tectonomagmatic pulses. What makes the Macquarie Arc special is not just its deposits, it's the complexity of its magmatic and tectonic history. Here, oceanic crust meets continental margin and created oxidized, hydrous, and fertile magmas. To unlock the whole potential of this mark, you need more than drills. You need zircon chemistry, structural mapping, and precise geochronology. If you compare it with the other arcs, we can say that Macquarie Arc of Australia is just like Andean Arc, and it's equivalent of Australia's Andean Arc. This map shows a Cowal igneous complex, which is a part of the Ordovician Macquarie Arc. The rocks here tell a rich story of subduction, crustal thickening, and multi-phase magmatism, which are ideal conditions for forming porphyry, gold, and copper systems. The Cowal district sits inside a fault-bounded crustal block, which is stretching over 40 kilometers. Most of it is buried under post-mineral sediments. So explorers rely heavily on geophysical mapping and deep drilling to understand what lies beneath those sediments. Key structures here like the Bouberoy Fault and Marsden alignment are more than boundaries. They're deep crustal pathways that focus magma ascent and ore-forming fluids. In the northern Cowal district, we see a string of low sulfidation epithermal gold deposits, which are hosting more than 9.6 million ounces of gold. New core from E41, which is one of these high sulfidation epithermal deposits, reveals seam mineral diorite porphyries with magnetite banded coarse veins and chalcopyrite veinlets, which are classic indicators of porphyry style copper and gold mineralization. And south of the alignment porphyry systems, and the head south of the Marsden alignment, you have large porphyry copper and gold with over 120 million tons at 0.46% copper and 0.27 gram per ton gold. Intrusions here range from early monzodiorite to seam mineral granodiorite porphyries. And then nearby at E43 and Milli, we see mineralized breccias, stockwork veins, and chalcopyrite tourmaline replacements. And now comes a cutting-edge tool for exploration of this area, which is Zircon geochemistry. By using laser ablation ICP-MS and trace element mapping, researchers measured oxidation state, temperature, and water content across individual zircon grains. So this is not just a geology map, it's a strategy guide, and target along crustal scale structures like the Marsden alignment focus on diorite and granodiorite porphyries, and using zircon zoning and chemistry can help to vector toward fertile magmas. Here we have some photos of hand samples or drilling core samples, and if you compare these samples with other porphyry deposits, we can see some unusual features. First of all, in plate A, we have an abundant equigranular texture in syn and pre-mineral units. Usually, typical porphyry intrusions show porphyritic textures with plagioclase and quartz phenocrysts. So these equigranular textures are not usual, they're unusual, and they're common even in mineralized phases like granodiorite and monzodiorite. And this suggests more evolved or homogenized magmas or deep-seated, slowly cooled magma batches, which are not typical for porphyry systems, and they often form in shallow level dikes or apophyses. The next is the presence of coarse cemented breccias with euhedral clasts in plates B and C, We have granodiorite clasts, which are euhedral and cemented by quartz feldspar matrix. These clasts supported angular breccias, or more typical of pre-mineralization intrusions, or pre-mineral breccias. But here they occurred during or near mineralization. This may indicate early fracturing and pressure cycling in the Cowal system, which are probably driven by deep magma chamber recharge. The next is presence of tourmaline breccias and tourmaline veins in plate G. Tourmaline-bearing breccias exist in some porphyry systems. You can find them in porphyries of Chile, like El Salvador, but they are not universal. And Cowal samples show abundant tourmaline associated with pyrite, chalcopyrite, and carbonate. And this suggests Cowal had a boron-rich hydrothermal phase, which potentially sourced from evolved magmas or crustal contamination. Again, it's not common in many porphyry settings and could signal a distinct fluid chemistry in this area. The next thing is presence of magnetite as both alteration and vein fillings. You can see that in plate D. Magnetite alteration halos are visible, which is quite common in early potassic zones of porphyry systems. But in Cowal we have magnetite, which appears both in veins and as replacement halos, often overprinting earlier textures. And this suggests strong oxidized phase post-dating veining rather than being purely syn mineralization. And we also have transition toward epithermal textures. Multiple samples show banded coarse veins, carbonate veins, and vein halos of tourmaline and pyrite, like in plates F and G. These are more epithermal-like than typical deeper porphyry veins, and this supports the chapter's conclusion that Cowal represents a transitional porphyry epithermal environment with telescoping fluid pathways. And finally, the last thing is a lack of typical B-type quartz veins. Classic porphyry copper systems usually show B-type quartz, chalcopyrite, and molybdenite veins with sericitic halos, but in Cowal those veins are less obvious, or maybe they have been replaced by more complex and texturally mixed vein styles, possibly due to multiple intrusion events and overlapping alteration zone. Most porphyry-related zircon studies rely only on discrete spot analyses. What is unique about this study is that they used rastered laser ablation, ICP-MS, and they used line scans across the entire zircon. You can see them in panel B, which created a high-resolution elemental map. And this approach allows a pixel-by-pixel interrogation, which is in panel D, and producing spatial distribution maps of different elements like uranium, titanium, and europium. So why it matters? This method captures zoning and also gross rims and resorption zones, which are often missed in point analysis, and they are quite critical for identifying magmatic evolution and fluid changes at high temporal resolution. Another interesting thing is that we have high uranium rims with low uranium cores in these samples, which is a kind of reverse of the usual trend. In many porphyry systems, zircon cores have higher uranium, and rims are depleted due to crystal aging and melt evolution. Here you can see in panel D that the outer rim has a slight higher uranium content, and while the core is moderate to low uranium. This reversal suggests that later stage magmas were more evolved, and they were possibly felsic or fluid saturated, and they were enriched in incompatible elements like uranium, and they were more oxidized or water rich, which are quite consistent with metal fertility. And this is unusual and aligns with Cowal's model of multi-pulse hybrid magmas evolving toward ore-forming conditions. And the last key feature in these images is that we have a complex CL zoning, cathodoluminance zoning, and patchy growth domains in panel A. The CL image shows oscillatory and sector zoning, but also patchy textures, including embayed growth zones and potential resorption surfaces. This suggests a dynamic open system magma, which could repeatedly affected by recharge with new magmas, or fluctuations in oxidation or melt, composition, rapid zircon dissolution, and resorption cycles. This level of zoning complexity is more commonly seen in arc adjacent and cross-contaminated systems, and it further supports Cowal's unique setting at the boundary between intraoceanic and continental arcs. And we also have zircon mapping as a magma fertility tool. It's not just a dating, and in opposite to most porphyry studies, in which zircon is used for geochronology and maybe some element profiles, here it's used as a multidimensional fertility tool. We have uranium in zircon for melt evolution, titanium contents for temperature, europium ratios for redox and plagioclase saturation, and we have thorium, uranium, and lanthanum ytterbium for fluid melt interactions. So this is the next generation approach to porphyry exploration geochemistry. Here in panel A, you can see a photomicrograph of pre-mineralization milli granodiorite. It features a textbook zircon, apatite, and titanite assemblage. Zircon is a robust crystallizer and trace element recorder. Apatite is sensitive to fluorine, chlorine, REs, and phosphorus availability. And titanite is common in oxidized systems, often linked to magnetite stability and hydrothermal stages. So the co-crystallization of all these three suggests moderately oxidized water-rich magmas, which have fertile conditions for copper and gold porphyry development. In panel B, we have a composite image of zircon from milli which is showing internal zoning and a large apatite inclusion. This pairing reflects early apatite saturation in the melt, likely indicating high phosphorus content and early RE partitioning. In panel C, we have zircon from E43 porphyritic granodiorite, which is revealing a large apatite inclusion and complex oscillatory zoning with resorption boundaries, which are highlighted by dashed lines. These textures point to episodic crystallization, which are interrupted by magma recharge or fluid influx. In panel D, we have zircon from E41 diorite porphyry. Again, it's showing apatite inclusions and pronounced dissolution surfaces. And this suggests that zircon crystallized through multiple magma pulses, and each was chemically distinct and may have been partially dissolved and regrown, possibly during hydrothermal overprinting. So why this is unusual and important? Apatite inclusions in zircon are not always this common or so large. Their presence and size point to early crystallization of phosphate-rich minerals. It's a good sign of volatile-rich metal-transporting magmas. And the complex zoning and dissolution textures in zircon indicate that Cowal's magmas were not static. They were evolved, mixed, and recharged over time. And this is not typical of single pulse porphyry systems. It suggests multi-phase, dynamic, magmatic evolution, more akin to continental arc settings, even though Cowal formed in a transitional arc environment. Here we have geochemical results of zircons. In panel A, we have comparison of gadolinium ytterbium and with the europium ratios. So why these ratios? Because gadolinium and ytterbium track RE fractionation, and europium ratios reflect plagioclase crystallization and melt oxidation. So what's interesting here is distinct fertile zircon field, which appears in the upper left in the shaded gray area, where europium ratios are more than 0.35 and gadolinium ytterbium are less than 0.07. Only zircons from C mineralization E41 and E42, E43 plot here as green triangles and red diamonds. Pre-mineralization Marsden and milli zircons fall outside this field. The lower europium ratios with higher gadolinium and ytterbium, and they're suggesting less evolved or less oxidized melts. So this plot alone can help identify fertile intrusive phases by itself. Then we have panel B, which is gadolinium ytterbium versus thorium uranium ratios, and they are both redox sensitive proxies. What stands out in this diagram? We have C mineralization zircons trends toward low gadolinium ytterbium and intermediate thorium uranium, and again clustering separately from pre-mineral zircons. These trends may reflect progressive rare earth depletion and fluid melt interactions in evolving magmas. Then we have panel C, which is FMQ versus ratios of cerium neodymium divided by yttrium. Delta FMQ estimates oxidation state relative to the phyolite magnetite quartz buffer. The x-axis here, cerium neodymium yttrium, combines RE behavior and melt fractionation. What does it show? It shows that seam mineralization F43 and F41 zircons plotted delta FMQ more than +1 with moderate cerium neodymium yttrium values, and it's a clear high oxidation signature. So Marston and milli zircons plot lower. You can see the show oxidation state is a key discriminator here. And we have panel D, which is delta FMQ versus europium ratios. So finally we come to the full circle, oxidation vs europium anomaly. The key insights here are that zircons from fertile intrusions, again E43 and 43 and 41 and 43, they cluster at high europium and high FMQ values, which are ideal for copper gold porphyry formation. And for Marston zircons, we have lower oxidation and lower europium ratios, which is a textbook example of a non-fertile intrusive unit. And why this matters? These plots don't just describe zircon chemistry, they offer a toolkit to access fertility in porphyry systems. We can use gadolinium yttrium versus europium ratios to find evolved oxidized melts. We can use FMQ and thorium uranium to track redox evolution across multiple magma batches, and we can map all these patterns back to the intrusive phases. And you're not just guessing anymore, you're just targeting, you're just defining targets for drill holes. Here we have much more trace element results in the zircons. This first chart looks at zircon chemistry, things like how much europium, gadolinium, and other rare earth elements they hold. And it's not just data; it's a chemical fingerprint for magma fertility. The fertile intrusions show high europium and low gadolinium yttrium ratios. Again, they shows crystallization from oxidized evolved melts, which are perfect for these porphyries. And the barren ones, they have lower europium and higher gadolinium yttrium. They're lacking chemistry needed to carry metals. And then we have oxidation state. We have FMQ, and see that the only fertile zircons show strong redox signals, the kind that you need to mobilize copper and gold. Now we add temperatures, which are measured from zircon's titanium content. And here's the twist. Hotter melts were not just hotter, they were more evolved, more oxidized, and better at concentrating metals. These magmas formed zircons with low hafnium and rising gadolinium yttrium, and they're tracing a path through fractionation, oxidation, and fluid saturation. Meanwhile, the cooler magmas, they show less RE fractionation, lower oxidation, and almost no sign of metal potential. So, what's the difference between these two figures? The one tells you who is fertile, which intrusion is fertile, is the chemistry-based fingerprint. And the others tell you how and when they became fertile through temperature evolution. And putting them together, you have a map to buried gold systems. Here we have CL images of zircons from monzodiorite, which is for the Marsden, and you can see the beautiful sector zoning. It doesn't look like that, but SZ1 here is a core and SZ2 is a rim. And then we have the mineral maps and the ratios. And that's a fancy way of showing how the light rare earth elements stack up against the heavy REs. You can see that in the panel B with cerium neodymium versus yttrium ratio. The outer rim here, it lights up in orange and red, and that means enrichment and LREs like cerium and neodymium. And why does that matter? Because LRE enrichment is a classic sign of a magma that has been evolving and staying oxidized, exactly the kind of conditions that can carry copper and gold. And in panel C we have hafnium zirconium ratios. Hafnium loves to stay in the melt longer than zirconium. So when this ratio climbs, it's a signal that melt is getting more fractionated and more evolved. And guess what? The red and orange zones toward the rim, they show just that. Evolved, oxidized, and ready to precipitate metal-rich fluids. Then we have panel D, which is gadolinium yttrium ratio. Here we've got gadolinium over yttrium, which are both heavy rare earth elements, and lower values on the rim tells us that the melt is changing, likely flattening its heavy RE profile. Not the strongest fertility signal, but it adds to the story of a dynamic evolving magma chamber. In panel E we have europium ratios, and we are looking at europium anomaly. This ratio tells us how much europium plus 2 got pulled into plagioclase during crystallization. In oxidized magmas, europium stays at europium plus 3, and it's less likely to get trapped in early plagioclase crystals. That means more is left behind to enter into the zircon crystals. And what do we see here is orange and red zones, especially toward the rim, which suggest a weak or suppressed europium anomaly. So this means that magma was oxidized and early water rich, which are two hallmarks of porphyry fertility. Another quiet but compelling clue that this zircon grow in a magma that had the right chemistry to carry copper and gold. In panel F, we have thorium over europium. Zircons from oxidized magmas love to show high thorium uranium ratios, usually values over 0.3, and that's exactly what we see in the core. The rim drops a bit, which could mean rising uranium and more fluids and just a final evolution step. So to wrap up this slide and put it all together, this zircon grain checks nearly every box for a fertile porphyry system. It grew in an oxidized melt with evolved geochemistry or chemistry, and shows trace element trends that mirror what we see in systems like Oyo Tolgoi and El Salvador. Here we have the final slide, which is a conclusion of what we saw in this paper. So, how do porphyry copper gold systems come to life? We have stages 1 to 2, which are located within deep crust with temperatures more than 850 to 750. It starts deep, way down in the crust. Hot mafic melts rise and mix with continental crust in what is called the mash zone. This is where the first zircon cores begin to crystallize. They're simple in texture, but they're holding the chemical blueprint of the system's roots. And then we have a transition to stage 3 and 4. They're shallow crust. Temperatures could be 800 to 700 degrees. And as magma rises, they evolve, cooling, degassing, and becoming more oxidized. These upper crustal levels are where the action really kicks off. Zircon crystals here develop complex rims, a chemical signal that melt is fertile, oxidized, and metal charged. And each zircon growth stage from core to rim is a kind of time capsule. The textures and trace elements tell us not just when the magma evolved, but where the fertile ore forming conditions took hold. So what are the exploratory keys? First of all, we have zircons with core to rim zoning in europium ratios and gadolinium yttrium ratios. Then we have complex zircon textures formed at upper crustal levels with geochemical signatures of oxidized and water-rich melts. Syn mineralization zircon rims linked to stockwork winning and fluid release. And we saw that zircons are not just minerals, they are microscopic messengers from deep time. And by decoding their chemistry and textures, we get a vertical map of the entire magmatic system from mash zones to mineralization. Thanks for watching.